Hello there and welcome to Scientific Serenity. Everything you hear here is carefully researched and prepared for you. Now, take a deep breath. Let the darkness become gentle. Before we begin, you may notice your body starting to relax. A gentle yawn may arrive. Your breathing may slow. As this story unfolds, your mind will drift naturally towards sleep. By the middle of this journey, rest will come quietly, and when you wake, you may feel calmer, because tonight, you fell asleep through science and learned something most people never will. If you see me as someone from your own family who researches and prepares this knowledge for you, subscribing, liking, and leaving a comment would truly mean a lot to me. And let the story begin. There is a color so deep that it has no reflection. A color that does not bounce light back to the waiting retina but swallows it whole, converting photon into heat, visibility into absence. This color has many names in many languages: Negro, Noir, Schwartz, Kuro, but in the language of biology, it has only one: eumelanin. And nowhere in the animal kingdom is this pigment expressed with more elegant precision than in the fur of Felis catus, the domestic cat, in its most mysterious and misunderstood manifestation, the black cat. Consider for a moment what it means to be black in a world built on light. Every object you see, every color you perceive, is merely reflected photons, light bouncing off surfaces and striking your retina at specific wavelengths. A red apple is red because its surface absorbs most wavelengths and reflects those around 700 nanometers. A blue sky is blue because air molecules scatter short wavelengths more efficiently than long ones. Color is not a property of objects. It is a conversation between light and matter, a negotiation mediated by the physics of reflection and absorption. Black is the object that refuses to negotiate. Black is the surface that says, "I will give you nothing back." All photons, all wavelengths, all colors, absorbed, converted, erased. This is the first paradox of the black cat. It is most visible precisely when it is trying to be invisible. In bright sunlight, a black cat's silhouette is absolute, its edges sharp against any background. It does not blend, it announces. It declares its presence through absence, through the hole it tears in the visual field. But as the light fades, as the sun dips below the horizon and the world descends into the soft, gray uncertainty of dusk, that same absence becomes camouflage. In the dim light of evening, when human vision struggles to distinguish shapes and boundaries, the black cat does not reflect what little light remains. It becomes one with the shadows. It disappears into the negative space between street lamps. This is not magic. This is physics. This is eumelanin, doing what eumelanin has done for millions of years. The molecule itself is astonishingly simple. It is a polymer, a long chain of repeating units, built from the amino acid tyrosine through a series of enzymatic reactions that occur in specialized cells called melanocytes. These cells, nestled at the boundary between the dermis and epidermis of the cat's skin, extend branching processes called dendrites into the growing hair follicles. There, they inject packets of melanin, melanosomes, into the keratinocytes that will form the hair shaft. The density, size, and distribution of these melanosomes determine the final color of the fur. In black cats, the melanosomes are large, numerous, and packed with eumelanin in its most concentrated form. They are arranged in a continuous layer throughout the hair cortex, ensuring that every photon entering the hair is absorbed before it can bounce back out. This is engineering at the molecular scale. This is nanotechnology, evolved. But here is where the paradox deepens. That absolute black, that perfect absorption is not permanent. Under certain conditions, prolonged sun exposure, nutritional deficiencies, the simple passage of time, the black cat's fur begins to change. It rusts. The phenomenon is called rusting in the language of cat fanciers, though scientists prefer the more prosaic color fading. Patches of the cat's coat, particularly on the back and flanks, take on a reddish-brown tinge, as if the animal has been lightly dusted with iron oxide. In some cats, the effect is subtle, visible only in certain lights. In others, the transformation is dramatic, turning a formerly black cat into something that resembles a chocolate-point Siamese. What causes this rusting? The answer lies in the fragile chemistry of melanin itself. Eumelanin, for all its light-absorbing power, is surprisingly vulnerable to photodegradation. When exposed to ultraviolet radiation, the same UV that tans human skin and causes sunburn, the long polymer chains of eumelanin begin to break. The bonds that hold the molecule together are cleaved by high-energy photons, fragmenting the continuous absorber into smaller pieces that reflect light differently. The result is a shift from deep black to reddish brown, the color of pheomelanin, the pigment responsible for red and yellow fur. In effect, the sun is bleaching the cat, not to white but to rust. But sunlight is not the only culprit. Nutrition plays a role as well. The enzyme that catalyzes the final step in eumelanin synthesis, tyrosinase, requires copper as a cofactor. Without adequate copper in the diet, tyrosinase cannot function efficiently, and the production of new melanin slows. When a rusting cat sheds its UV-damaged fur and grows new hair, that new hair may contain less eumelanin than the old, perpetuating the rusty appearance. This is the second paradox. The black cat's darkness depends on light, not just for its visibility but for its very existence. Without sunlight to drive the evolution of melanin's protective properties, without copper to enable its synthesis, without the complex interplay of genetics and environment that determines its expression, the black cat would not be black at all. It would be something else, something less, something visible. To understand the genetics of black fur, we must first understand the concept of dominance. In the simple Mendelian genetics taught in introductory biology courses, dominant alleles mask recessive ones. A cat with one copy of the black allele, B, and one copy of the chocolate allele, B, will appear black because black is dominant over chocolate. This is true as far as it goes, but it does not go nearly far enough. The reality of feline coat color genetics is far more complex, far more fascinating, and far more revealing of the deep relationship between appearance and physiology. The gene responsible for black fur in cats is officially designated TYRP1, tyrosinase-related protein 1. It sits on chromosome D4, a specific location in the cat genome that has been mapped, sequenced, and analyzed in laboratories around the world. The protein it encodes is one of several enzymes involved in the melanin synthesis pathway, working in concert with tyrosinase and other factors to convert tyrosine into eumelanin. When the TYRP1 gene is functioning normally, when its DNA sequence is intact and its expression is properly regulated, the result is black fur. But genes are not static, they mutate. And mutations in TYRP1 produce a range of interesting effects. The most common mutation, known as B lowercase to indicate recessiveness, disrupts the enzyme's function partially, resulting in brown or chocolate fur. A more severe mutation, BL, produces cinnamon, a lighter, warmer brown. Cats with two copies of these mutant alleles, B/B or BL/BL, cannot produce full eumelanin. Their fur is various shades of brown rather than true black. But here is the crucial point: black is the default. Black is what happens when nothing goes wrong. The TYRP1 gene in its ancestral form produces black fur. The mutations that produce brown and cinnamon are losses of function, breakdowns in the elegant machinery of melanin synthesis. This means that every black cat is, genetically speaking, a purist. It carries the original version of the gene, the version that has been passed down through millions of years of feline evolution. Its darkness is not an aberration but a heritage, a direct line to the ancestral cat that first emerged from the African wildcat some 10,000 years ago. But there is more. Recent research has suggested that the TYRP1 gene, and the melanin it helps produce, may have functions far beyond mere coloration. Consider the immune system. Melanocytes, the cells that produce melanin, are derived from the neural crest, a population of embryonic cells that also gives rise to parts of the nervous system, certain bone and cartilage structures, and, significantly, cells involved in immune function. Some researchers have proposed that the genetic pathways regulating melanin production are intertwined with those regulating immune response, and that selecting for black coat color may inadvertently select for enhanced disease resistance. This is not as far-fetched as it sounds. In chickens, studies have shown that dark-feathered individuals are more resistant to certain bacterial infections than their light-feathered counterparts. In humans, melanin is known to bind to toxins and pathogens, potentially reducing their harmful effects. And in cats, anecdotal evidence from breeders and owners suggests that black cats may be hardier, longer-lived, and less prone to certain diseases than cats of other colors. The mechanism, if it exists, is not fully understood. Melanin might act as a sink for free radicals, reducing oxidative stress and its damaging effects on cells. It might modulate the immune response directly, altering the behavior of immune cells. Or the genetic variants that produce black fur might be linked, through the phenomenon of linkage disequilibrium, to other variants that enhance immune function, purely by accident of chromosomal proximity. Whatever the mechanism, the possibility is intriguing, that the black cat's darkness is not merely a color but a signal, a visible marker of underlying physiological strength. That when we look at a black cat, we are not seeing absence but presence. The presence of a robust immune system encoded in pigment. This is the third paradox. Black is health. Black is resilience. Black is the color of survival. Let us now enter the fur itself. Not as an observer but as a traveler, shrinking ourselves to microscopic scale, descending into the landscape of the hair shaft, exploring the structures that transform biology into color. The first thing you would notice at this scale is the geometry. A cat's hair is not a simple cylinder but a complex structure with multiple layers. The outermost layer, the cuticle, consists of overlapping scales, like shingles on a roof, that protect the inner cortex. These scales are transparent, made of keratin, the same protein that forms human fingernails and rhinoceros horns. They do not contribute to color. They simply transmit light to the layers beneath. Below the cuticle lies the cortex. This is where the action happens. The cortex is packed with melanosomes, those pigment-containing organelles, embedded in a matrix of keratin. In a black cat, the melanosomes are densely distributed throughout the cortex, their eumelanin content so high that they appear as solid black rods under the electron microscope. They are oriented parallel to the long axis of the hair, maximizing their light-absorbing efficiency. At the very center of the hair, in some cat breeds, lies the medulla, a central core of loosely packed cells that may contain air spaces. The medulla's primary function is insulation, trapping air to help regulate the cat's body temperature. In black cats, the medulla is often less developed than in other colors, possibly because the melanin-rich cortex already absorbs so much solar radiation that additional insulation is unnecessary. This is thermal engineering at the microscopic level. The black cat's fur is not merely a covering. It is a solar collector, a heat-trapping blanket, a thermodynamic marvel. Now consider the texture. Black cat fur is often described as silky or velvety, and there is a reason for this. The density of melanosomes affects not only color but also the mechanical properties of the hair. Melanin is a stiffening agent. It reinforces the keratin matrix, making each hair more resilient, more resistant to breakage. A black cat's coat, all else being equal, may be physically stronger than a white cat's coat, simply because of what it contains. This is not speculation. Studies of human hair have shown that melanin content correlates with mechanical strength. Darker hair is harder to break than lighter hair. The same principle likely applies to cats. And then there is the phenomenon of ghosting, the faint, almost imperceptible pattern of tabby stripes that can sometimes be seen on black cats in certain lights. This is not a trick of the eye, it is a genetic echo. The gene for black fur, the B allele at the TYRP1 locus, does not erase the tabby pattern. It simply overrides it, flooding the hair with so much eumelanin that the pattern becomes invisible under normal conditions. but in very bright light or at certain angles, the underlying tabby architecture can sometimes be glimpsed, a ghost of the cat's ancestral coloration haunting the edges of its darkness. This ghosting is most pronounced in young kittens, whose melanin production has not yet reached full capacity. A black kitten may show distinct tabby markings that fade as it matures, its coat darkening to uniform black by adulthood. The pattern is still there, encoded in the DNA, waiting to be expressed. But the melanin machinery, once fully operational, drowns it out. This is the fourth paradox. The black cat carries within itself the image of what it would be if it were not black. Its darkness is a veil, drawn over a more colorful reality. Underneath the eumelanin, underneath the genetic dominance, underneath the centuries of selection for this particular shade of absence, there is a tabby cat waiting to be seen. The final mystery of the black cat's color is the one that touches us most directly, our response to it. Why are we drawn to darkness? Why do black cats, despite centuries of superstition and persecution, continue to capture our imagination? Why do they appear in our art, our literature, our folklore? Sometimes as omens of evil, sometimes as companions of witches, but always as figures of power and mystery. The answer may lie in the very nature of vision itself. Human eyes are not evenly sensitive to all colors. Our retinas contain 3 types of cone cells, each tuned to a different wavelength range: short blue, medium green, and long red. Together, these cones allow us to perceive the full spectrum of visible light. But they are not equally distributed. The medium and long wavelength cones, the ones that detect green and red, are far more numerous than the short wavelength cones. Our eyes are optimized for the colors of daylight, the greens and browns and blues of the natural world. Black is not a color, it is the absence of color. It stimulates none of our cone cells. It is, for our visual system, a null signal, a gap in the sensory field that the brain must interpret. And the brain, confronted with absence, does what it always does. It fills in the gap with meaning. This is where the 5th paradox emerges. Black cats are not inherently mysterious. They are simply dark. The mystery is in us, in the way our brains process absence, in the stories we tell to explain what we cannot see, in the ancient, deep-seated human tendency to project meaning onto the unknown. Consider the phenomenon of pareidolia, the tendency to perceive familiar patterns, especially faces, in random stimuli. It is pareidolia that makes us see a man in the moon, a face in a cloud, a figure in the shadows. And it is pareidolia, amplified by the absence of visual information, that makes a black cat in dim light seem somehow more than a cat, more aware, more intentional, more connected to the darkness that hides it. We see 2 golden eyes floating in the gloom, and our brains immediately construct a presence around them. The cat becomes a witness, a guardian, a spirit. Its blackness, which is simply an absence of reflected light, becomes a presence of another kind, a presence of potential, of possibility, of the unknown. This is why black cats have been both revered and reviled throughout human history. They are canvases onto which we project our deepest fears and highest hopes. In ancient Egypt, where cats were first domesticated, the black cat was associated with the goddess Batet, a protector of the home, a guardian against evil spirits. To kill a black cat was a capital offense. To own one was to invite divine favor into your household. In medieval Europe, that same darkness became sinister. The black cat, already associated with the night and the unseen, was reimagined as a familiar of witches, a shape-shifting demon, a servant of Satan. Thousands of black cats were killed during the witch hunts, their bodies burned alongside those of the women accused of consorting with them. And yet, in other cultures, the black cat retained its protective status. In Japan, the Maneki Niko, the beckoning cat figurine believed to bring good luck, is often depicted as black, a color associated with warding off evil and attracting prosperity. In parts of Scotland, a black cat appearing on your doorstep is a sign of impending wealth. On ships, black cats were kept as good luck charms, believed to ensure safe passage through treacherous waters. The same animal, the same darkness, the same absence of light, but different stories, different meanings, different worlds. This is the final lesson of the melanin paradox. That color is not a property of objects but a relationship between objects and observers. The black cat is black regardless of who looks at it. But what that blackness means, whether it signals health or sickness, luck or danger, mystery or menace, depends entirely on the eyes that see it. And now, as you drift towards sleep, imagine those eyes. Not the cat's eyes, though they are watching, always watching, but your own. Imagine closing them, letting the darkness behind your lids merge with the darkness of the room, letting the boundary between self and world dissolve into the soft, absolute black of a sleeping cat's fur. The cat breathes beside you. Its chest rises and falls in the ancient rhythm of mammalian sleep. Its purr vibrates at frequencies that heal bone and calm nerves. Its darkness absorbs not only light but also worry, not only photons but also fear. You are safe. You are warm. You are not alone. The invisible engineer of the night is at work, building something you cannot see, in a language you cannot understand. But you can feel it, the weight of its presence, the depth of its silence, the endless, patient darkness of its fur. There is a place inside the eye where light goes to die. It is called the retina, that thin layer of neural tissue at the back of the eyeball, no thicker than a page of this book, where photons are converted into electrical signals and the raw data of vision begins its journey to the brain. In the human retina, light passes through this layer once, strikes the photoreceptor cells, the rods and cones, and is absorbed. Most of it anyway. Some photons slip through, passing between the photoreceptors or bouncing off the back of the eye without being captured. These lost photons are wasted, their information discarded, their potential to illuminate the world forever extinguished. The human eye is, in this sense, a place where light comes to die. But it is also a place where light comes to be wasted. The cat's eye is different. In the cat's eye, light does not die when it reaches the retina. It is resurrected. Behind the retina, pressed against the back of the eyeball like a mirror laid beneath a painting, lies a structure that has no equivalent in the human visual system. It is called the tapetum lucidum, Latin for bright tapestry, and it is one of the most extraordinary examples of biological engineering in the natural world. The tapetum lucidum is a reflective layer. Its function is simple: to catch the photons that slip through the retina without being absorbed and bounce them back for a second chance. Light enters the eye, passes through the retina, strikes the tapetum, and is reflected back onto the photoreceptors from behind. Each photon gets 2 opportunities to be captured, 2 bites at the apple, 2 chances to contribute to the image forming in the cat's brain. This is the secret of night vision. This is why cats can see in what we would call total darkness. This is why their eyes glow when caught in a beam of light. But the tapetum lucidum is not merely a mirror. It is an adaptive, tunable, chemically complex structure whose properties can change in response to lighting conditions. It is not a single organ but a family of structures, varying across species, optimized for different visual niches. And in the domestic cat, it has reached a pinnacle of refinement that rivals anything in human engineering. Structurally, the feline tapetum lucidum is what biologists call a tapetum cellulosum, a layer of flattened cells arranged in rows like tiles on a roof, each cell packed with reflective crystals. These crystals are composed of riboflavin, vitamin B2, and zinc. They are arranged in precise geometric arrays, their orientations calculated to maximize reflection at the wavelengths most useful for nocturnal vision. The color of the tape-tau reflection varies from cat to cat, ranging from brilliant green through golden yellow to deep blue. This variation is determined by the thickness of the tape-tau layer, the density of the crystals, and the amount of pigment in the overlying retina. Some cats have eyes that glow emerald in the dark. Others burn with the light of ancient gold. No 2 are exactly alike. Each tapetum is as individual as a fingerprint, and it is not static. The tapetum lucidum can adjust its reflective properties in response to light levels. In bright conditions, the cat's pupil contracts to a vertical slit, reducing the amount of light entering the eye. At the same time, pigments in the tape-tau cells may shift, slightly reducing reflectivity to prevent the retina from being overwhelmed. In darkness, the pupil expands to a perfect circle, flooding the eye with available light, and the tapetum maximizes its reflective efficiency, squeezing every possible photon from the surrounding gloom. This is not merely vision. This is visual processing at the edge of physical possibility. This is biology operating at the quantum limit. To understand what the world looks like through a cat's eyes, you must imagine a universe built from light so faint that human vision would perceive only formless gray. The dimmest starlight, the last vestiges of twilight, the ghostly glow of distant city lights scattered by high clouds. These are the photons that cats weave into detailed images of their world. Every faint gleam is captured, reflected, captured again. Every photon is wrung dry of its information before being finally, reluctantly, absorbed. The result is not merely better night vision than humans possess. It is a fundamentally different kind of vision, a mode of seeing that operates in a light regime we cannot even perceive. Let us now enter the cat's eye, not as metaphor but as journey. Let us shrink ourselves to the scale of photons, to the size of the individual quanta of light that carry information about the world. Let us ride those photons through the cornea, through the pupil, through the lens, and into the profound darkness of the vitreous humor, the gel that fills the eyeball. And let us witness what happens when light meets the tapetum lucidum. The first thing you would notice at this scale is the architecture. The tapetum is not a smooth surface but a textured one, its cells arranged in overlapping layers that create a complex three-dimensional landscape. Each cell is packed with those reflective crystals, riboflavin and zinc, arranged in precise crystalline arrays. The spacing between crystals is not random. It is tuned to the wavelength of light that most stimulates the cat's rod cells. This is photonic engineering at the molecular level. The tapetum is, in effect, a distributed Bragg reflector, the same technology used in modern fiber optics and laser cavities, but evolved over millions of years and encoded in biological tissue. When a photon strikes this crystalline array, several things can happen. It can be reflected directly, bouncing back toward the retina along a path roughly parallel to its incoming trajectory. It can be scattered, its direction randomized, increasing the chances that it will encounter a rod cell on its return journey. Or it can be absorbed by the tapetal cells themselves, its energy converted into heat. A last resort, a fail-safe, a way of preventing the eye from becoming overwhelmed by excessive light. The efficiency of this system is astonishing. Measurements of tapetal reflectivity in domestic cats show that between 30 and 50% of the light striking the tapetum is reflected back onto the retina. This effectively doubles the light available to the photoreceptors, giving the cat a two-stop advantage over humans in low-light conditions. But the tapetum's contribution goes beyond mere reflection. The orientation of the crystals is such that they preferentially reflect light at the peak sensitivity of the cat's rod cells, around 500 nanometers in the blue-green part of the spectrum. This is not coincidence, it is adaptation. The tapetum is tuned to the cat's visual system, optimized to enhance the wavelengths that matter most for nocturnal vision. Now consider the rods themselves. The human retina contains approximately 120 million rod cells, the photoreceptors responsible for vision in dim light. This sounds like a lot, and it is. But the cat's retina contains roughly the same number of rods in an eye that is significantly smaller. The density of rods in the feline retina is approximately twice that of the human retina. More rods per square millimeter means more light-gathering power, more sensitivity, more information extracted from each photon. But density is not the only factor. The cat's rods are also longer than human rods, their outer segments, the light-sensitive portions, extending further into the pigment epithelium. This increased length provides more surface area for photopigment molecules, increasing the probability that any given photon will be absorbed. And the photopigment itself, rhodopsin, is subtly different in cats. Its peak sensitivity is shifted slightly toward the blue end of the spectrum, matching the wavelengths that dominate the night sky. A starlit landscape is rich in blue light. The cat's eyes are optimized to capture it. Add it all together: the tape tau reflection, the rod density, the rod length, the spectral tuning. The result is a visual system that can function in light levels approximately 6 times dimmer than the human threshold. Where we see only darkness, cats see detail. Where we are blind, they hunt. Why do cats' eyes glow? It is a question that has fascinated humans for as long as we have shared our homes with these animals. Ancient Egyptians, who worshipped cats and mummified them by the millions, must have wondered about the green fire that burned in their companions' eyes at night. Medieval Europeans, already inclined to see demonic influence in anything they did not understand, took the glowing eyes as proof of diabolical connection. Children throughout history have been simultaneously terrified and delighted by the sight of two floating lights in the darkness, approaching with silent purpose. The answer, as we have seen, is the tapetum lucidum. But the question deserves a deeper answer, an answer that addresses not only the mechanism but the meaning. When you see a cat's eyes glowing in the dark, you are not seeing light produced by the cat. You are seeing light that originated elsewhere: a distant street lamp, a rising moon, the headlights of a passing car, reflected back to you after being captured and amplified by the cat's visual system. The cat's eyes are beacons, but they are passive beacons. They shine only because something else has shone first. This is why cats' eyes do not glow in absolute darkness. If there is no light source, if you are in a completely blacked out room with no windows, no cracks under doors, no electronic indicators on appliances, the cat's eyes will not glow. The tapetum has nothing to reflect. The cat can still see better than you can because its visual system is more sensitive and because there is always some light, however faint, that human eyes cannot detect. But the characteristic glow requires an external source. The color of that glow varies, as we noted earlier, from cat to cat. But it also varies with the angle of observation, the wavelength of the incident light, and the state of adaptation of the cat's eyes. A cat whose pupils are fully dilated, adapted to deep darkness, will have a different tape tau reflection than a cat that has just emerged into dim light from a bright room. The tapetum is not a static mirror but a dynamic system, its properties shifting with the visual demands of the moment. This variability has led to centuries of folklore about cats with different colored eyes, or eyes that change color depending on the phase of the moon. The truth is less mystical but no less fascinating. The tapetum lucidum is a living tissue, responsive to its environment, adapting second by second to optimize the cat's vision. Now, consider what this means for the cat's experience of the world. Human vision is designed for the day. Our retinas are optimized for bright light, high resolution, and color discrimination. We see the world in rich chromatic detail, but we pay for this privilege with poor night vision. When the sun goes down, we become effectively blind, dependent on artificial light, on memory, on other senses to navigate our environment. Cats are different. Their visual system is optimized for the boundary between day and night, the crepuscular hours when their prey is most active. They see well in bright light, though with less color discrimination than humans. But they see spectacularly in dim light, in the gray hours of dawn and dusk when the world belongs to hunters. This is why cats are most active at these times. This is why they sleep through the middle of the day and the middle of the night, rousing themselves to patrol their territories and hunt their prey in the transitional hours. Their eyes, with their tapetum and their dense rods and their spectral tuning, are built for twilight. And those glowing eyes, floating in the darkness of your bedroom at 3 a.m., are not eerie or supernatural. They are simply the most efficient light-gathering instruments ever evolved, doing what they were designed to do, extracting every possible photon from the dimmest of environments, building a visual world from light you cannot even see. The final mystery of the tapetum lucidum is not how it works but why it exists at all. After all, evolution could have taken a different path. It could have produced cats with larger eyes like owls, sacrificing other aspects of skull architecture for increased light-gathering ability. It could have produced cats with more sensitive rod cells, pushing the limits of phototransduction even further. It could have produced cats that were simply less active at night, shifting their behavior to times when light is more abundant. But evolution did none of these things. Instead, it produced the tapetum lucidum, a structure that solves the problem of low-light vision not by gathering more light but by using the available light more efficiently. This is a fundamentally different strategy, and it reveals something profound about the evolutionary history of cats. The ancestors of modern cats were small, solitary hunters, competing with much larger predators for food and territory. They could not afford to be large. Large bodies require more food, more territory, more resources. They could not afford to be strictly diurnal. The day belonged to bigger, faster, more dangerous animals. They could not afford to be strictly nocturnal. The night belonged to owls and snakes and other specialists. So they became crepuscular, active at dawn and dusk, the boundary times when light is dim but not absent, when the advantages of superior night vision could be leveraged without the full commitment to darkness. And they evolved the tapetum lucidum, a lightweight, low-cost, highly efficient solution to the problem of seeing in twilight. No need for giant eyes that would weaken the skull. No need for exotic photopigments that might compromise color vision. Just a simple reflective layer behind the retina, giving each photon 2 chances to be captured. This is the genius of evolution. It finds the elegant solution, the minimal intervention that produces maximum effect. The tapetum lucidum is not a workaround or a compromise. It is a masterpiece of biological engineering, a structure that does exactly what it needs to do, no more and no less, with a parsimony that human engineers can only envy. And now, as you drift toward sleep, imagine that you are the mouse, not the predator, the prey. Imagine yourself in a moonless field, surrounded by darkness so complete that you cannot see your own feet. You are small, vulnerable, entirely dependent on your senses to detect the approach of danger. You hear nothing. You smell nothing. The night is empty, but you feel something. A presence. A weight in the darkness that was not there a moment ago. You freeze. Your heart hammers against your ribs. Your ears strain for any sound, your nose for any scent. There is nothing. Then you see them. Two circles of green-gold light, floating in the darkness, approaching with silent purpose. They are not reflecting anything. There is nothing to reflect. They are simply glowing, generated from light so faint that your eyes cannot register its source. They are the eyes of the hunter, and they are looking directly at you. This is what it means to be prey in a world of tapeta lucida. This is the nightmare that has driven the evolution of escape responses in small mammals for 60 million years. This is the terror encoded in the genes of every creature that has ever frozen at the sight of glowing eyes in the darkness. But you are not the mouse. You are the human, safe in your bed with a small warm weight curled at your feet. That weight breathes slowly, rhythmically, its chest rising and falling in the ancient pattern of mammalian sleep. Its eyes are closed, the tapeta hidden behind lids that flicker occasionally with the movement of dreams. In those dreams, the cat is hunting. It is stalking through tall grass, its body low to the ground, its eyes fixed on prey that only it can see. The tapeta glow with reflected moonlight, gathering every photon, building a world of detail from the dimmest of illuminations. The muscles coil, the haunches bunch, the tail twitches. And then the cat wakes, briefly lifts its head, looks at you with eyes that no longer glow but simply reflect the soft light of your bedside lamp. It blinks slowly once, twice. Then it settles back into its curl, its head on its paws, its breathing deepening, its dreams resuming. You are not prey. You are not the mouse. You are the one the cat trusts, the one it chooses to sleep beside, the one whose presence means safety rather than danger. And in that trust, in that choice, lies something profound. The cat, with its tapeta and its rods and its million-year heritage of nocturnal hunting, has decided that you are not a threat, that you are, in fact, a comfort, that your bed is warm enough, your presence reassuring enough, your heartbeat steady enough to justify closing those extraordinary eyes and surrendering to sleep. The tapetum lucidum rests. The rods and cones idle. The visual system, that masterpiece of biological engineering, powers down for the night. And the cat dreams. There is a clock inside every living thing. It is not made of gears and springs, not powered by batteries or electricity. It is built from genes and proteins, from feedback loops that oscillate with the precision of quartz, from molecular mechanisms that have been refined by evolution for billions of years. This clock is the circadian rhythm, the internal timekeeper that synchronizes an organism's biology with the daily cycle of light and dark on a rotating planet. In humans, this clock is set to a roughly 24-hour cycle, and it governs everything from our sleep-wake patterns to our hormone secretion to our body temperature. We are diurnal creatures, optimized for activity during the day and rest at night. Our circadian rhythm reflects this heritage, promoting wakefulness when the sun is high and sleep when darkness falls. Cats are different. The feline circadian rhythm is not aligned with the human day. It is not even aligned with a simple nocturnal or diurnal pattern. Cats are something else entirely. They are crepuscular. The word comes from the Latin crepusculum, meaning twilight. Crepuscular animals are those that are most active during the twilight hours, dawn and dusk, when the light is dim but not absent, when the world belongs neither to the day nor to the night. This is the cat's natural time, the hours for which its visual system was designed, the window when its prey is most vulnerable and its predators most constrained. But the cat that shares your home, the cat that sleeps on your bed and eats from a bowl and has never hunted for its survival, still carries this ancient clock in its genes. And that clock does not care that you work a 9 to 5 job. It does not care that you need 8 hours of uninterrupted sleep. It does not care that 3 a.m. is, for humans, a time for deep rest and dreamless unconsciousness. At 3 a.m. the cat's crepuscular rhythm says, "Wake. Hunt. Feed." This is the source of the zoom eyes. This is why your peaceful night's sleep is interrupted by what sounds like a small horse galloping through your living room. This is why cats, after hours of apparent deep sleep, can suddenly explode into frenetic activity for no observable reason. The zoom eyes, formerly known in veterinary behavior literature as frenetic random activity periods, or FRAPs, are not random at all. They are the expression of pent-up energy, the release of hunting drive that has been suppressed by domestication and indoor living. In the wild, a cat would spend its twilight hours stalking, chasing, pouncing, killing. Each of these activities requires explosive bursts of energy, carefully timed and precisely executed. The cat's body is designed for this. Powerful hind legs for launching, flexible spine for twisting mid-air, claws that extend and retract with surgical precision. But the indoor cat has no prey. Its food comes from a can delivered by a human hand. Its hunting drive has no outlet. So the energy accumulates, building throughout the long hours of human-imposed inactivity, until something triggers its release. That something might be a sound, a movement, a flicker of light. Or it might be nothing at all, simply the internal pressure of accumulated drive exceeding the threshold of containment. And then the cat runs. Not toward anything, not away from anything. Just runs because running is what a cat's body was built to do at twilight, and twilight has arrived whether the cat is outdoors or in. This is the first lesson of the crepuscular rhythm. Behavior that seems inexplicable from a human perspective makes perfect sense when viewed through the lens of evolutionary history. The cat is not being annoying, it is being a cat. It is not trying to wake you. It is simply responding to the ancient clock that ticks in every cell of its body. To understand why cats sleep so much, 12 to 16 hours per day on average, with some individuals reaching 20, we must understand something fundamental about the predator's energy budget. Hunting is expensive. The stalk, the chase, the pounce, the kill, each of these activities consumes calories at a prodigious rate. A wild cat may spend only a few hours per day actually hunting, but those hours require peak physical performance, explosive power, and intense concentration. The rest of the day must be devoted to conserving energy, to sleeping and resting and digesting, to being ready for the next opportunity to hunt. This is the predator's paradox. The more successful you are at hunting, the less you need to hunt. A kill provides enough food to sustain you for many hours, even days. But to make that kill, you must be at your physical peak when the opportunity arises. So you sleep, you rest, you conserve, you wait. Domestic cats have inherited this pattern, even though their food comes from bowls rather than blood. Their metabolism is still that of a predator, designed for feast and famine, for explosive output followed by deep recovery. When your cat sleeps 16 hours a day, it is not being lazy. It is being efficient. It is storing energy for the hunt that, in its evolutionary memory, is always just around the corner. But not all sleep is the same. Mammalian sleep consists of two fundamentally different states: non-REM sleep and REM sleep. Non-REM is the deep, restorative sleep during which the body repairs itself, growth hormone is released, and energy stores are replenished. REM, rapid eye movement, is the sleep state associated with dreaming, with memory consolidation, with the processing of emotional experiences. Cats experience both, and they experience them in proportions that reveal something about their cognitive lives. The cat sleep cycle is shorter than the humans, approximately 25 to 30 minutes, compared to the human 90-minute cycle. Within each cycle, the cat spends about 70% in non-REM sleep and 30% in REM. This means that over the course of a 16-hour sleep day, a cat may spend nearly 5 hours in the dream state, far more than humans who typically dream for about 2 hours per night. Why so much dreaming? The leading theory is that REM sleep plays a crucial role in processing the complex spatial and motor information required for successful hunting. During REM, the brain replays recent experiences, consolidating memories of successful strategies and discarding irrelevant information. The cat that dreams of chasing is literally practicing the chase, strengthening the neural pathways that will be needed when real prey presents itself. This is why sleeping cats move. The twitching whiskers, the paddling paws, the occasional vocalization. These are not random spasms but the physical expression of dream content. The cat is running in its sleep, stalking in its sleep, pouncing in its sleep. Its body is rehearsing movements that its waking self may never need but that its evolutionary self cannot forget. There is a famous series of experiments from the 1960s in which researchers selectively deprived cats of REM sleep. The results were striking. Cats deprived of dreaming became hyperactive, hypersexual, and disoriented. They lost the ability to learn simple tasks. Their immune systems weakened. Some died within weeks. Dreaming, it turns out, is not optional. It is not a luxury or a byproduct. It is a biological necessity, as essential to the cat's functioning as food or water. The cat that sleeps 16 hours a day is not wasting time. It is performing the most important work of its life, the work of being a cat. Let us now enter the cat's dream. Not as scientists, not as observers, but as participants. Let us imagine ourselves shrinking to the scale of neural activity, riding the electrochemical impulses that cascade through the sleeping brain, witnessing the internal world that the cat constructs from memory and instinct and the raw data of experience. The first thing you would notice is the geometry. The sleeping brain is not quiet. It is alive with coordinated activity. Waves of neural firing sweep across the cortex in regular rhythms, their frequency and amplitude changing with the sleep stage. During REM, these waves become chaotic, desynchronized, resembling the waking brain more than the sleeping one. This is the signature of dreaming. The cortex is active, processing information, but that information is not coming from the senses. It is coming from memory. In the cat's dream, the world is built from fragments. A scent remembered from last week's exploration of the garden. The feeling of sun on fur from a nap taken months ago. The sound of a bird that was never caught, replayed and analyzed and replayed again. These fragments are woven into narratives that follow the logic of emotion rather than the logic of reality. The cat dreams of hunting. Always hunting. Even cats that have never killed, never stalked, never tasted blood dream of hunting. The pattern is encoded too deeply to be erased by domestication. In the dream, the cat stalks through tall grass that does not exist, stalks prey that has never been seen, executes pounces that end in captures that are always successful. But sometimes the cat dreams of other things. Of the warm lap where it sleeps, of the hand that feeds it, of the voice that calls its name. These dreams are softer, less intense, suffused with the feeling of safety rather than the thrill of the chase. In these dreams, the cat does not hunt. It rests. It purrs. It is content. The balance between hunting dreams and comfort dreams varies from cat to cat, influenced by genetics, experience, and the quality of the cat's relationship with its humans. Cats that feel secure, that trust their environment, that have positive associations with their human companions, these cats dream more of comfort. Cats that are anxious, that have experienced trauma, that live in unpredictable environments, these cats dream more of hunting. The dream life is a window into the emotional state, a nightly report on how the cat is coping with its world. And then, sometimes the dream becomes nightmare. Veterinary behaviorists have documented what appears to be REM sleep behavior disorder in cats, a condition in which the normal paralysis that accompanies REM sleep fails, allowing the cat to physically act out its dreams. A cat experiencing this will suddenly sit up, eyes open but unseeing, and engage in complex behaviors. Hissing, growling, swatting at invisible opponents, fleeing from non-existent threats. The cat is not awake, it is still dreaming. But its body is responding to the dream content as if it were real. These episodes are distressing to witness and potentially dangerous for the cat, which may injure itself by running into furniture or falling from heights. They are also, for scientists, a window into the intensity of the feline dream life. The cat that thrashes and hisses in its sleep is experiencing something so vivid, so compelling, that its body cannot help but respond. Most cats, fortunately, remain safely in the paralysis of REM. Their dreams play out entirely within the theater of the mind, their bodies still, their whiskers twitching, their paws paddling gently at air that offers no resistance. The final mystery of the crepuscular rhythm is the one that touches us most directly, the relationship between the cat's sleep and our own. We share our homes with an animal whose biological clock is fundamentally different from ours. We sleep when it wants to hunt. We wake when it wants to rest. We seek the bright light of day. It seeks the soft gloom of twilight. And yet, somehow, we have learned to coexist, to find common ground in the narrow windows when our rhythms overlap. That overlap occurs primarily at the boundaries. In the early morning when the cat's dawn activity coincides with our awakening. In the evening when the cat's dusk hunting drive meets our return from work. These are the times when cats are most interactive, most affectionate, most present. These are the times when the ancient bond between human and feline is most visibly expressed. But what about the night? What about the hours when the cat's crepuscular rhythm says, hunt, and our circadian rhythm says, sleep? The answer lies in accommodation. Cats are adaptable. Their circadian rhythms are not rigid. They can shift in response to environmental cues, including the behavior of their human companions. A cat that learns that 3 a.m. zoom eyes result in being shut out of the bedroom may eventually adjust its activity patterns. A cat that discovers that quiet waiting at the bedside brings morning treats may learn to suppress its hunting drive until dawn. This is not domestication in the genetic sense. That process took thousands of years and is now complete. This is individual learning, moment-by-moment adaptation, the ongoing negotiation between two species sharing a single space. And it works, most of the time. But sometimes, despite all adaptation and accommodation, the cat's crepuscular rhythm asserts itself with irresistible force. The energy accumulated through 16 hours of sleep and rest and dreaming reaches a threshold that cannot be contained. The hunting drive, suppressed but not extinguished by domestication, demands expression. And the cat runs. The zoom eyes are not a failure of domestication. They are not a sign that the cat is unhappy or poorly adjusted. They are simply the overflow of a system designed for a different world. A world of tall grass and hidden prey and the perpetual risk of becoming prey oneself. In that world, the ability to switch from complete stillness to explosive action in an instant was not a quirk. It was survival. In our world, it is a minor annoyance, a momentary disruption of sleep, a story to tell at work the next day. But it is also a reminder, the creature sleeping at our feet, purring in contentment, dreaming of chases it will never run, is not entirely domesticated. Part of it still belongs to the twilight, to the hunt, to the ancient rhythm that has governed feline existence for 40 million years. And that part, no matter how deeply buried, will occasionally emerge. At dawn, at dusk, at 3 a.m. for no apparent reason, the cat will remember what it is. It will run. It will chase. It will be, for a few glorious minutes, exactly what evolution designed it to be. Then it will return to your bed, curl at your feet, and sleep. The clock will reset. The cycle will begin again. There is a face in every shadow. This is not mysticism, it is neuroscience. The human brain is wired to find patterns, and the most important pattern it can find, the most survival-relevant pattern in the entire history of primate evolution, is the face. A face means a conspecific, a potential ally, a potential threat. A face means social information, emotional cues, the possibility of communication. The brain is so dedicated to finding faces that it sees them where they do not exist. In clouds, in rock formations, in the pattern of knots on a wooden door. This phenomenon is called pareidolia, and it is one of the most powerful perceptual biases in the human cognitive toolkit. Now consider the black cat. In dim light, the light of dusk, the light of dawn, the light of a room lit only by embers, the cat's body disappears. Its black fur absorbs the available photons, reflecting nothing back to the waiting eye. But its eyes do not disappear. The tapetum lucidum ensures that the eyes catch what little light exists and throw it back amplified toward any observer. What the observer sees then is not a cat. What the observer sees is two glowing eyes, floating in darkness, apparently unattached to any body. And those eyes are not randomly arranged. They are spaced exactly as eyes should be spaced, at the width of a typical mammalian face. They are oriented forward, suggesting a predator rather than prey. They blink slowly, deliberately, with the unhurried confidence of a creature that knows it is being watched. The brain, presented with this visual stimulus, does what it always does. It looks for a face, and it finds one. Not the cat's face, that is invisible, erased by darkness, but the suggestion of a face, the implication of a face, the ghost of a face. The brain constructs a presence around those eyes, a presence that is more than a cat, more than an animal, more than a physical entity. The brain creates a watcher. This is the psychological foundation of every myth, every superstition, every cultural narrative about black cats. We do not project meaning onto them arbitrarily. We project meaning onto them because their appearance in low light triggers the most fundamental pattern recognition systems in our brains. They become, literally, faces in the darkness, and faces demand interpretation. The interpretation varies across cultures and epochs, but the underlying mechanism is universal. A creature that appears as disembodied eyes is automatically perceived as mysterious, as powerful, as connected to realms beyond the visible. It is not quite of this world. It belongs, somehow, to the world of spirits, of ancestors, of gods. This is why black cats have been worshipped and persecuted in equal measure. This is why they appear in the iconography of goddesses and the familiars of witches. This is why, in 1,000 folk tales across 100 cultures, the black cat is never just a cat. It is always something more: a messenger, a guardian, an omen, a guide. The cat, of course, knows nothing of this. It sits in the darkness, blinking slowly, its tapetum glowing with reflected light. It is not trying to be mysterious, it is simply being a cat. But its biology, evolved for nocturnal hunting, has accidentally tapped into the deepest structures of human perception. It has become, without intent or awareness, a symbol, and symbols have power. The story begins in Egypt, not at the beginning of cat domestication. That probably happened earlier in the Fertile Crescent, where wild cats first approached human settlements to hunt the mice that were attracted to stored grain. But in Egypt, the relationship between humans and cats achieved a level of intimacy and reverence unmatched in any other ancient culture. The Egyptian word for cat was myo, onomatopoeic, derived from the sound cats make. It was one of the first words Egyptian children learned to speak, and it was also one of the last words whispered to the dead, inscribed on amulets placed in tombs to protect the deceased on their journey through the underworld. The goddess Batet, depicted as a lioness or as a woman with the head of a lioness, was the divine embodiment of the cat's dual nature. She was a protector, a guardian of the home, a defender against evil spirits and disease. But she was also a warrior, a fierce lioness who could destroy her enemies with terrifying efficiency. In her, the Egyptians recognized what every cat owner knows, that the creature sleeping peacefully in your lap is also a predator capable of killing with cold precision. Bastet's cult center was at Bubastis in the Nile Delta, where a vast temple complex housed thousands of cats tended by priests. Pilgrims traveled from across Egypt to offer gifts to the goddess and to have their prayers conveyed through her feline intermediaries. When a cat died, its body was mummified with the same care as a human's, wrapped in linen and placed in a specially decorated coffin. To kill a cat, even accidentally, was a capital offense. Why such reverence? The practical answer is obvious. Cats protected Egypt's grain stores from rodents, preserving food that meant the difference between survival and starvation. But the symbolic answer runs deeper. Cats, with their glowing eyes and silent movement and apparent ability to see in darkness, seem to inhabit two worlds simultaneously, the world of the living and the world of the spirits. They walk the boundary between day and night, between the visible and the invisible, between the human realm and the realm of the gods. This liminal quality, this ability to exist at thresholds, made them ideal guardians. In Egyptian theology, the most dangerous moments were transitions. Dawn and dusk, birth and death, the passage from life to afterlife. At these thresholds, the boundaries between worlds grew thin, and malevolent spirits could slip through. Cats, as creatures of the threshold, could see these spirits and drive them away. This is why Egyptian families kept cats in their homes, not merely as mousers but as spiritual guardians. The cat that slept at the foot of your bed was not just a pet, it was a protector watching over you while you slept, defending you from forces you could not perceive. And when the black cat appeared among them, fully black without markings, its fur absorbing light like a hole in the world, the Egyptians saw something special. Black was the color of fertility, of the rich Nile silt that brought life to the desert. Black was the color of the underworld, of the regenerative darkness from which new life emerged. A black cat was not an omen of evil. It was a concentration of the most powerful forces in the universe, a living amulet against harm. 3,000 years later, in medieval Europe, that same blackness would be reinterpreted as evil. But in Egypt it was holy. The fall of the black cat from sacred to sinister is one of the great tragedies of cultural history. It began subtly with the spread of Christianity through the Roman Empire. The early church, seeking to distinguish itself from pagan traditions, systematically demonized the symbols and practices of the religions it displaced. The Egyptian gods, including Batet, were recast as demons. The animals associated with them, including cats, were tainted by association. But the real transformation occurred in the medieval period, when a series of social and theological developments converged to make the black cat a symbol of absolute evil. The first was the Cathar heresy in southern France. The Cathars were a dualist sect that believed the material world was created by an evil god and that salvation lay in rejecting the physical. The church, seeking to destroy the Cathars, accused them of worshipping a cat that appeared at their secret meetings. A black cat, naturally, that was the devil in disguise. This accusation, repeated endlessly in sermons and inquisitorial documents, entered the popular imagination and stuck. The second was the witch hunts. As fear of witchcraft spread across Europe in the 15th through 17th centuries, the black cat became firmly associated with witches and their practices. Witches were said to keep familiar spirits, demons in animal form, that assisted them in their magic. The most common form for these familiars was the black cat. To see a black cat at night was to see a witch's spy, gathering information for its mistress, preparing some malevolent act. The third was the Black Death. When bubonic plague swept through Europe, killing a third of the population, people looked for scapegoats. Cats, already associated with darkness and witchcraft, were obvious targets. They were killed by the thousands, thrown into fires, massacred in rituals of purification. The irony is bitter. Cats are natural predators of rats, and rats carried the fleas that transmitted plague. By killing cats, Europeans ensured the survival of more rats and the spread of more disease. Superstition defeated pragmatism, and millions died as a result. In this atmosphere of fear and persecution, the black cat's fate was sealed. Its glowing eyes, once signs of divine protection, became evidence of demonic possession. Its silent movement, once admired as grace, became proof of sinister intent. Its darkness, once associated with fertility and regeneration, became the color of death and damnation. The cat, of course, did not change. It was the same animal that had curled in the lap of Egyptian pharaohs, that had guarded Japanese temples, that had kept mice from Roman grain stores. But the human interpretation changed, and with it, the cat's fate. Thousands of black cats died in the witch hunts, burned alongside the women accused of consorting with them. Thousands more were killed in casual acts of cruelty, their darkness marking them as targets. Even today, some animal shelters report lower adoption rates for black cats, and many refuse to adopt them out around Halloween, fearing they will be used in ritual abuse. The black cat survived. It always survives. But it carries the weight of these centuries of fear, a weight encoded not in its genes but in the human response to its presence. In Japan, the black cat found redemption. The Japanese relationship with cats has always been complex and nuanced. Cats arrived in Japan from China or Korea, probably accompanying Buddhist monks who brought sacred texts and, inadvertently, the rodents that threatened them. The monks valued cats as protectors of the scriptures, and this association with sacred texts gave cats an aura of holiness from the beginning. But the black cat's particular status in Japan derives from a different source. The maneki neko, the beckoning cat figurine that welcomes customers into shops and restaurants throughout the country. The maneki neko is typically depicted as a calico cat, white with patches of black and orange, raising one paw in a gesture that resembles beckoning. But black maneki neko exist too, and they have their own significance. A black maneki neko is believed to ward off evil spirits and protect its owner from harm. It is, like the cats of ancient Egypt, a guardian against malevolent forces. Why black for protection? The answer lies in Japanese folklore and its treatment of darkness. In Shinto tradition, darkness is not inherently evil. It is simply the absence of light, a space where spirits, both benevolent and malevolent, can move unseen. A black cat, being itself dark, can move through this space undetected by malevolent spirits. It can see them, but they cannot see it. It becomes, in effect, an invisible guardian, patrolling the boundaries between worlds without alerting the dangers that lurk there. This is the opposite of the European interpretation. In Europe, the black cat's darkness made it suspect, aligned with the forces of evil. In Japan, that same darkness makes it powerful, aligned with the forces of protection. The same biological trait, black fur that absorbs light, is interpreted through completely different cultural lenses, producing completely different meanings. And there is more. Recent behavioral research, though still preliminary, suggests that black cats may indeed form stronger bonds with their human companions than cats of other colors. The data is not definitive, sample sizes are small and confounding variables are many, but the pattern is intriguing. Several studies have found that owners of black cats report higher levels of attachment, more frequent affiliative behaviors, and greater satisfaction with the human-cat relationship. Why might this be? One possibility is selection bias. People who choose black cats may be more committed, more willing to look beyond superficial appearance, more likely to invest time and energy in the relationship. Another possibility is that the same genetic factors that produce black fur may also influence temperament, though this is speculative. A third possibility, the most interesting to my mind, is that the experience of sharing life with a creature that has been so misunderstood, so persecuted, so unfairly judged creates a special bond. The owner and the cat become allies against an unjust world, their connection deepened by shared experience of prejudice. Whatever the explanation, the phenomenon is real. Ask any owner of a black cat and they will tell you, their cat is special. Their cat is more attentive, more affectionate, more attuned to their emotional state than any cat they have known. Their cat is a guardian, a protector, a friend. And perhaps they are right. Perhaps 40 million years of evolution, 10,000 years of domestication, and 3,000 years of cultural projection have produced in the black cat something genuinely unique. An animal that is simultaneously a predator and a companion, a symbol and a being, a creature of darkness and a bringer of light. The cat that sleeps at your feet, its black fur absorbing the soft glow of your bedside lamp, its purr vibrating at frequencies that heal your stress-weary bones, its eyes occasionally opening to check on you with that slow, deliberate blink that means trust. This cat is the inheritor of all those histories. Egyptian temples and European witch hunts, Japanese shrines and medieval massacres, all of it converges in this single warm, breathing presence. It does not know its own history. It does not need to. It simply is what it has always been. A small predator, a companion, a guardian of the threshold between sleep and waking, between light and dark, between the world we see and the world we sense but cannot name. And when you look into its glowing eyes in the darkness of your bedroom, you are not seeing a demon or a goddess or an omen. You are seeing a creature that chose 10,000 years ago to share its life with yours. You are seeing the result of that choice, repeated across millennia, refined by evolution, perfected by cohabitation. You are seeing a friend. There is a frequency at which bones grow stronger. It is not a metaphor, it is a measurable physical phenomenon. When bone tissue is subjected to mechanical stress, the stress of weight-bearing exercise, the stress of vibration at specific frequencies, osteoblasts, the cells that build bone, become more active. They lay down new matrix, increasing bone density and strength. This is why astronauts lose bone mass in microgravity. Without the constant stress of Earth's gravity, their skeletons begin to dissolve. The frequencies that most effectively stimulate bone growth are low, between 25 and 150 Hz, in the range of what we perceive as deep vibration rather than audible sound. And remarkably, this is exactly the frequency range of a cat's purr. Domestic cats purr at frequencies ranging from about 20 to 140 Hz, with a fundamental frequency typically around 25 to 30 Hz. This is not accidental, it is adaptive. The purr evolved as a form of communication between mother cats and kittens, a way of signaling safety and contentment in the darkness of the den where visual signals were useless. But like many evolutionary adaptations, it has acquired secondary functions. Functions that benefit not only the cat but those who share its life. Research has shown that exposure to frequencies in the 20 to 50 Hz range can increase bone density and promote fracture healing. Studies on animal models and human patients have demonstrated accelerated recovery from bone injuries when the affected area is subjected to low-frequency vibration. The mechanism appears to involve the stimulation of osteoblasts and the increased production of growth factors that promote tissue repair. Now consider what happens when a cat purrs on your chest or on your lap or curled against your side. The vibrations of its purr are not confined to its own body. They transmit into yours, traveling through skin and muscle and bone, stimulating your tissues at those same healing frequencies. Every time a cat purrs on you, it is literally performing physical therapy on your body. This is not pseudoscience, it is biomechanics. The cat's purr is a biological ultrasound machine, evolved over millions of years, tuned to the frequencies that promote healing in mammalian tissues. And it operates automatically whenever the cat is content, whenever it feels safe and comfortable and bonded. But bone healing is only the beginning. The same frequency range that stimulates osteoblasts also appears to promote soft tissue healing. Tendons, ligaments, muscles, all respond to mechanical vibration by increasing protein synthesis and accelerating repair. Wounds heal faster when exposed to low-frequency vibration. Swelling decreases, pain diminishes, and then there are the effects on the nervous system. The purr is not just a mechanical vibration. It is also a sound, an auditory stimulus that the brain processes in specific ways. The low, rhythmic quality of the purr is inherently calming, triggering parasympathetic nervous system activity and reducing the production of stress hormones. Cortisol levels drop, heart rate slows, blood pressure decreases. The body shifts from the fight or flight mode of sympathetic dominance to the rest and digest mode of parasympathetic relaxation. This is why cats are so effective at reducing human stress. This is why people who live with cats have lower rates of heart disease, lower blood pressure, better mental health outcomes. It is not just the companionship, though that matters. It is the vibration. It is the frequency. It is the purr. To understand the purr, we must first understand how it is produced. For decades, the mechanism of purring was a mystery. Early anatomists proposed various theories: that it resulted from turbulence in the blood flow through the vena cava, that it was produced by the vibration of the hyoid bone in the throat, that it was simply a voluntary muscle contraction with no special mechanism at all. None of these theories fully explain the phenomenon. The current understanding, based on advanced imaging and physiological studies, is that purring is produced by the rapid contraction and relaxation of the muscles within the cat's larynx, specifically the muscles that control the vocal folds. These muscles contract at frequencies between 25 and 150 times per second, causing the vocal folds to open and close with equal rapidity. Each closure produces a brief pulse of sound. The rapid succession of pulses merges into a continuous tone, perceived as a purr. What makes this remarkable is that the purring muscles are active during both inhalation and exhalation. Most vocalizations, meows, hisses, growls, occur only during exhalation, when air is flowing outward over the vocal folds. Purring occurs throughout the respiratory cycle, creating a continuous sound that can be maintained for hours without interruption. This requires extraordinary neuromuscular control. The cat's brain contains specialized neural oscillators that generate the rhythmic signals driving the laryngeal muscles. These oscillators are located in the hypothalamus and brainstem, deep in the primitive structures that regulate basic life functions. Purring is not a conscious choice, not entirely. It is an automatic response to specific emotional states, triggered by the same neural circuits that regulate contentment and social bonding. But the cat can modulate it. The frequency, the intensity, the duration of purring can be adjusted voluntarily, allowing the cat to use purring as a form of communication. A kitten purring to signal its location to its mother produces a different purr than an adult cat purring while being petted by its human companion. Cats in pain or distress may purr at slightly different frequencies than contented cats, suggesting that purring may also serve as a form of self-soothing, a way of calming the nervous system in times of stress. This is the genius of the purr. It is simultaneously automatic and controlled, reflexive and intentional, a product of deep evolutionary history and a tool for moment-to-moment interaction. It is the cat's way of saying without words what words could never express. I am safe. I am content. I am with you. And when you hear that purr, when you feel its vibration through your skin and into your bones, your body responds at levels below conscious awareness. Your nervous system recognizes the signal of safety. Your stress responses down-regulate. Your immune system shifts resources from preparation for injury to routine maintenance and repair. You become, quite literally, healthier than you were a moment before. Let us now enter the body at the cellular level. Not as observers, but as participants, as the very cells that are being affected by the cat's purr. Let us shrink ourselves to the scale of osteoblasts, of fibroblasts, of neurons and immune cells, and witness what happens when vibration at healing frequencies encounters living tissue. The first thing you would notice at this scale is the mechanotransduction. Cells are not passive blobs. They are dynamic structures, constantly sensing and responding to mechanical forces. Embedded in their membranes are proteins, integrins, cadherents, stretch-activated ion channels that detect physical deformation and convert it into biochemical signals. When the cat's purr vibrates through your tissues, these proteins are activated. They send signals to the nucleus telling the cell, mechanical stress is occurring. Respond appropriately. In osteoblasts, the response is increased production of bone matrix. The cells ramp up their synthesis of collagen and other proteins, laying down new tissue that will eventually mineralize into solid bone. In fibroblasts, the cells that build connective tissue, the response is similar. Increased production of extracellular matrix, accelerated wound healing, faster repair of damaged structures. In immune cells, the response is more complex. Macrophages, the scavenger cells that clean up debris and fight infection, become more active when exposed to low-frequency vibration. Their phagocytic activity increases. They engulf and destroy pathogens more efficiently. Lymphocytes, the cells that coordinate specific immune responses, show altered patterns of cytokine production, shifting the immune system toward a more balanced, less inflammatory state. And in neurons, the response is perhaps most important of all. The vibration of the purr stimulates the release of endorphins, the body's natural painkillers, and serotonin, the neurotransmitter associated with well-being and contentment. Pain signals are dampened. Mood improves. Anxiety decreases. The entire nervous system shifts toward a state of calm alertness, the state most conducive to healing and repair. This is why cats are used in animal-assisted therapy programs around the world. This is why nursing homes and hospitals and rehabilitation centers are increasingly incorporating cats into their therapeutic offerings. It is not just that cats are comforting. It is that cats, through the simple act of purring, deliver a precise, evolved, biologically optimized form of physical therapy. And black cats, with their dense coats and their often more robust physiques, may be particularly effective purr delivery systems. The melanin that darkens their fur also strengthens the hair shafts, making the coat denser and better at transmitting vibration. The same genetic factors that produce black fur may also influence the neural oscillators that control purring, potentially producing purrs of different frequencies or intensities. This is speculation, still unproven, but it aligns with what many black cat owners report, that their cats seem to purr more deeply, more resonantly, more healingly than other cats. Whether this is objectively true or simply another layer of the black cat's mythology, the effect is the same. When a black cat curls on your chest and purrs, you are receiving a therapy that no human invention can replicate. A therapy evolved over millions of years, refined by natural selection, delivered with unconditional feline affection. The final mystery of the purr is not how it works but why it exists at all. After all, purring requires energy. The rapid contraction of laryngeal muscles, sustained for hours, consumes calories that could be used for other purposes. In evolutionary terms, any trait that consumes resources must provide a compensating benefit, or it will be selected against and eventually disappear. What benefit does purring provide to the cat itself? The leading theory is that purring is a form of self-healing, a way for cats to maintain their own bone density and tissue health during the long periods of inactivity that characterize their lifestyle. Cats sleep 16 hours a day. During those hours, they are not weight-bearing, not exercising, not subjecting their skeletons to the mechanical stress that maintains bone density. Without some compensatory mechanism, they would be at risk for osteoporosis and other bone-weakening conditions. The purr may be that mechanism. By vibrating their own skeletons at frequencies that stimulate osteoblast activity, cats may be able to maintain bone health even during extended periods of inactivity. The purr is, in effect, an internal exercise machine, a way of tricking the bones into thinking they are bearing weight when they are not. This theory is supported by the observation that cats purr not only when content but also when injured, frightened, or in pain. Cats in veterinary clinics recovering from surgery will often purr for hours. Cats in labor purr. Cats near death purr. These are not situations of contentment. They are situations of stress and vulnerability. But they are also situations where tissue healing is urgently needed. The cat may be purring to accelerate its own recovery, to stimulate its own healing processes to survive. If this is true, then the purr is one of the most elegant adaptations in all of evolutionary biology. It is a self-healing mechanism that also serves as a communication signal. It benefits the cat directly, and it benefits those who share the cat's life indirectly. It is simultaneously selfish and altruistic, a product of individual selection that has acquired social functions through the accident of shared frequency. And for the human who shares a home with a cat, the purr is a gift beyond measure. It is a therapy delivered without prescription, without side effects, without cost. It is available anytime the cat chooses to offer it, which for most cats is most of the time. It is the sound of safety, the vibration of healing, the frequency of connection. The black cat that sleeps on your chest, its purr resonating through your sternum into your ribs and spine and the deep bones of your pelvis, is not just keeping you company. It is maintaining your skeletal health. It is reducing your stress hormones. It is stimulating your immune system. It is quite literally healing you with every breath it takes. And you, in return, offer warmth and safety and food and affection. You offer a lap to curl in, a hand to pet, a voice that speaks the cat's name with love. You offer the security that allows the cat to enter that vulnerable state where purring is possible. You are, in the deepest sense, partners in healing, two species separated by millions of years of evolution, brought together by the accident of domestication and the intentionality of choice, working together to keep each other healthy and whole.